We are towards the end or getting near the end of, I think, chapter 9. We talked about stoichiometry. We talked about basic stoichiometry problems. And remember, pretty much basic stoichiometry problems are pretty much most of the stoichiometry problems really follow 4 basic steps, which is none of it works if you don't have a balanced equation. You want to always convert whatever they give you to moles. And then the third step really is the sort of stoichiometry part. You go to the balanced equation. We use those coefficients as mole-to-mole relationships. And you go to the equation and get the mole-to-mole relationship that you're looking for. As we talked about, pretty much one of the relationships is obviously whatever they gave you. The other one is pretty much what you're looking to solve for. And lastly, you will always be in moles at this point. The last step here is a lot of times you do need to convert to some other unit. And really, these are really the 4 steps you should always follow when you're doing a basic stoichiometry problem, sort of regardless of how the information is given to you. We also talked about that there are sort of limiting reagent problems. And in limiting reagent problems, there's always a reactant that pretty much gets used up first in the reaction. And there's one that there's an excess amount of. And when it is a limiting reagent problem, you can really identify it by what is given to you. So you can identify it by if you are given enough information to calculate the moles of each reactant. That is basically a limiting reagent problem. And we really do still follow the same 4 steps. The additional sort of process in a limiting reagent situation is somewhere right around here, we need to figure out the limiting reagent. And there's really multiple ways you could do that. But the way we talked about was to do a simple sort of calculation between the 2 reactants and figure out how much of one reactant we need to use up the other reactant. And that's basically one way that you could do it. So you could basically do a calculation to figure out how much of the other reactant is needed to use up the first reactant, if you will. And when you do that calculation, you will get a number. It will be in moles, and it'll say like, hey, you need like 4 moles of this guy to use up the other reactant. And what you want to do is compare that to your starting amount and see if you have enough. And if you do have enough, then that means that that is the excess reagent. If you do not have enough, then that means it is the limiting reagent. The good news is, as we talked about, if you can identify one as the limiting or one as the excess, then the other guy is the opposite. All you have to do is basically identify one. So that's a very common way. Once you do that, the really important part is it is always the limiting reagent that determines how much product you make. So once you determine which one is the limiting reagent, it's important to go back and use the starting amount of that limiting reagent and then do another stoichiometry problem to figure out, how much product you would make, and that would be up to your theoretical yield in that case. We also did some problems and talked about that you can also figure out how much of the excess reagents left over by looking at how much you need of the excess and how much you start of it, and basically subtract the 2. So this is a common way that you could do it. Any questions first off on that there? I will say another very common way that people do limiting reagent problems is to simply just do 2 separate stoichiometry problems, starting with each reactant and going to the product that you're interested in. And then whichever one product is your limiting reagent, your theoretical yield. So that's an alternative approach that sometimes books will teach you, that you basically just do 2 separate calculations, starting with the first reactant and go all the way down to the product, and then do a second calculation with the second reactant again, doing a stoichiometry calculation to the product, and whichever one produces the least amount of product, again, would be your limiting reagent and your theoretical yield. So sometimes people just kind of do those two calculations separately, and that's another common way that you can kind of do that. There's like 3 or 4 different ways you could do these type of problems. Any questions on either of that? All right, so I think we did an example. So let us take a look at another example. This is the one I think we did at the end. All right, so why don't we try this one here? So starting with this, if we started with 622.7 grams of NH3, the molar mass is 1703 grams per mole from the periodic table. And CO2, molar mass is 4401 grams per mole. What is the limiting reagent? And calculate the mass of our product that is being formed. Here's the molar mass of this guy from the periodic table as well. And how much of the excess reagent will be left over. So why don't you take a few minutes here and work through it. So we're looking for how much will be produced, how much of the excess reagent will be left over in grams. And the molar masses are all given to you there. So that's pretty good. Okay, let's take a look, see how you're doing or progressing here. So we'll start with our same 4 steps here. We have our balanced equation. So let me rewrite it here. 2 of these guys plus a little CO2. Okay, and they do give us 622.7 grams of NH3. They also give us, looks like 1241 grams of CO2. So first off, is this a limiting reagent problem? This is, again, we're given grams of both of the reactants. So that is enough information to get us to moles of both of them. So that is the big flag that this is a limiting reagent problem. So we're still going to kind of really follow the first couple of steps there, which is our balanced equation. Really, the next thing we want to do is convert what they gave us into moles. So they were nice enough to give us the molar mass here. If they didn't, then obviously you'd go to the periodic table to get it. We'll do 1703 grams per mole for our NH3. And 4401 there for our CO2. That looks like for our NH3, we end up with we'll call it 36.565. We'll take a couple digits here, moles of NH3. 1241 divided by 4401 gets us 28,198, looks like. Any questions on that step there? This is, again, remembering our starting amount, right, that we are given. So because it's a limiting reagent problem, like I said, there's 2 ways. You can, if you want, at this point, just do 2 separate calculations to the product using the starting amount of each and figure out which one gives you the least. Or you could do a calculation like we talked about, where I'm going to, in this case, want to know if I want to use up all my NH3, how much CO2 I need. So how much CO2 is needed to use up all the NH3 we started with. So we're just going to do a little stoichiometry problem between those 2. So starting with my 36.565 moles of NH3, the mole to mole relationship from the equation for 2 moles of NH3, which is just the coefficient, I get 1 mole of CO2, which is also the coefficient from the balanced equation. Cancel. And that will give us, again, that 18.283 moles of CO2. Now would be more sense to actually compare it to the CO2 there. And in this case, we are still, we need 18.2 and we have 28. So we still have enough in this case. So that would mean that, again, this is our excess reagent in this case, and the NH3 here would be our limiting. Sorry about that. Any questions on that? Now that I didn't screw it up as badly there. Okay, so in this case, like I said, as long as you can determine one as your excess, by default, the other one's your limiting. So in this case, that does mean in this instance that it is the NH3 that is our limiting, and we would want to use the NH3 here. So going back to the starting amount of our NH3, which is this guy, 0.565 moles of NH3. We're now going to do our mole-to-mole relationship between NH3 and our product, which is a 2-to-1 relationship. 2 moles of NH3 and 1 mole of our product here. Going to get us basically our same number there, which is 18.283 moles of our product, which we can now, because that's what we're looking, which is technically filled in moles. And they gave us the molar mass of that as something 6006, I think. So using the molar mass from the periodic table, 6006 grams per mole will get us 1098 grams of our product, I think, in this case. Any questions on that there? That again would be our theoretical yield in this particular case. So again, it is really the same 4 steps, just this little added step in the middle there to figure out which one's a limiting reagent. Then don't screw it up like I did there and actually compare the right numbers there. And getting yourself there to our product. Any questions on that there? It also wanted to know, right, how much of the excess reagent would be left over. Since we chose the excess reagent that's left over at this point. Do that, it looks like, which is what we started with, minus our 18,283. So that again was how much was needed. That's how much we started with. And that tells us that we ended up with 28198 minus 18.283, about 9.915 moles of CO2 is left over, which we then can use the molar mass of CO2 to figure out how many grams that would be, which is obviously the same molar mass we used earlier. So times it by 4401 gives us, it looks like 436.4 grams CO2 left over. And that's good because we started with about 1,200 grams of it, right? So we got about 436 grams of it still left over when this reaction's over. As we talked about last time, if you perhaps didn't choose maybe the right calculation to figure out which one's the limiting reagent in terms of this, you would have to go back and sort of do this calculation here. If you actually didn't choose that one, you chose sort of the other reactant to do. So you sometimes do need to kind of go back and do that calculation between the 2 reactants. Any questions on any of those steps there? Question on limiting reagent problems. All right. Let's see. Okay, so that's good. That's better than I did, I suppose. There we go. All right, so let's talk a little about yield to reaction, which we touched upon sort of in lab, but it was officially talk about it. There's a few different types of yield. The first one is the theoretical yield, which is essentially what we've been calculating from the equation. The theoretical yield is always calculated from the balanced equation and pretty much how much you start with of the limiting reagent. And again, the theoretical yield really is your maximum yield. By the way, you can only do a theoretical yield. A yield about in terms of yields is what we're talking about here. The theoretical yield is your maximum yield. Again, that is like everything went. All your yellow wasn't stuck on your stirring rod or your beaker when you were doing an experiment like we did earlier. This is you should get. As we know, and as you saw in that particular experiment, not everything is perfect. You can't always get everything out of the beaker, the test tube, whatever it may be. You always kind of lose stuff along the way. So what we end up with is what you did when you reweighed your filter paper. You ended up with the actual yield, which is when you actually performed the experiment. That is actually how much of the product that you produced. In book problems and so forth, the actual yield is usually always given to you. So it's always given to you in some form. It'll say, hey, you actually produced this much or something like that. So the theoretical yield is one where we calculate like we've been doing either a basic stoichiometry problem or a limiting reagent type problem to calculate the theoretical yield. So in most problems, like I said, this is usually something you calculate, and this is usually something sort of given to you. And using both of those yields, the actual and the theoretical, that is where we get really a lot of times the important yield that most people are interested in, which is the percent yield. So the percent yield is basically taking both of those guys and dividing them. We take our actual divided by the theoretical times 100, and that gives us our percent yield. Percent yield, we do want high. This is great, We don't want it really above 100%, because although it may seem like that's a good thing, it's actually a bad thing in an experiment. If you get above 100% yield, you probably screwed up somewhere along the way. For example, if you remember when we did that experiment, we took the filter paper and let it really dry out, right? But if you were in a rush and you really didn't let it dry out and you reweighed the filter paper while it was still wet, you get a lot more water weight that really wasn't your product, and that would yield you a over 100% yield. So usually we don't want to go over 100% yield. In theory, it is possible, obviously, and it usually means you screwed up somewhere along the way in that experiment. But high 90s, low 90s and up, is really good yield. Again, if you got like a 5% yield, you also probably screwed up pretty badly there. All right, so let us skip this example here because I just don't feel like doing that one. I'll scroll it through in case you would like to see it. All right. Let's do this one here, which is kind of the same equation we were just using. So you can use the same molar masses and all that from that equation. 100 grams of ammonia is reacted with 100 grams of carbon dioxide. It produces 120 grams of our product here. What is the percent yield here? So we're looking for the percent yield. So as we just saw there, and we talked about before, percent yield is our actual divided by our theoretical, and we're going to times it by 100%. In this case, we're taking 100 grams of ammonia, mixing it with 100 grams of carbon dioxide, and we are producing 120 grams of our product here. So like I said before, typically in book problems, they will give you the actual yield, which is that guy right there. Here, we do need to figure out the theoretical yield. And when we look at it, we have 100 grams of ammonia and 100 grams of our carbon dioxide. So again, we're given the starting amounts of both reactants. So again, here, this is a limiting reagent situation because of that. So our first step here is done. We got our equation balanced. We're going to then kind of do the second step, which is convert what they give us into moles. So that's 100 grams of NH3. Using the molar mass that we had from the previous problem there, 1703 grams per mole. We'll also take the 100 grams of CO2 and use the molar mass that we saw from the previous one as well, 4401 grams per mole. And that gives us 100 divided by 1703. And that gives us, looks like 5.872 moles of NH3. Taking our 100 grams of CO2 and divided by 4401 gives us 2.272 moles of CO2. Again, this is really our starting amount. Any questions up to there? Yeah. This is the, these guys here are the molar mass from the periodic table. So go and just add up for the one nitrogen at 1401 and the, where we got there 3 hydrogens at 1.008. Yeah. Other questions? Okay, so again, like we did before, I'm going to take one of them. So here, and try not to screw it up this time, but I'm going to go and try to figure out again how much CO2 is needed to use up again all of the NH3. So starting with my NH3 here, 5.872 moles of NH3. Same mole to mole relationship since we're using the same equation, 2 moles of NH3, 1 mole of CO2, again from the balanced equation and the coefficients. That is not the plus, but the actual coefficient there. That is where we're getting that from. So 5.872 divided by 2 gives us 2.936 moles of CO2 is needed. Now I'm going to actually, I think I got that right this time. So we're going to actually go and compare with the moles of CO2 that we are starting with. So I need 2.9 moles of it. I'm starting with 2.2. Do I have enough in this case? I do not. So I do not have enough. That means in this particular problem, it is actually the CO2 here is the limiting reagent, and our NH3 here is our excess reagent here. Any questions on that determination? At this point, now that we've determined our limiting reagent, we want to take the starting amount of our limiting reagent here and figure out how much of our product there we would produce. So I'll flip a page here. So starting with our 2.272 moles of CO2, we're going to do now a mole to mole relationship between the CO2 and our product, which should be, I believe in this case, a 1-to-1 relationship, right? So that is a 1 mole of CO2 to 1 mole of our product. And that would give us 2.272 moles of our product here. That would be, again, technically our theoretical yield in moles. But we don't really want it in moles because our actual yield's in grams, so that all the units cancel out correctly. We're going to now convert this into grams. So 2.272 moles of NH2CO using the molar mass that was nicely given to us in the last one. 6006 looks like. And again, that comes from the periodic table. Gets us about 136 grams of our product would be produced. That again is the theoretical yield in grams. Any questions on that there? All right, so what is left here is actually to calculate the percent yield. So our percent yield going to be our actual, which I believe they said was 120 grams, right? Divided by our theoretical, which is 136 grams, times it by 100. So 120 divided by 136 times it by 100 gets us approximately 88.24%. Not terrible, I suppose. Any questions on any of those steps there? Yeah. with 4 in the problem, so that's what I ended up with 0.0, or 20.0. Yeah. Questions on that? Questions on stoichiometry, limit reagents, percent yields, actual yields? You know how to do all that? All right, so that pretty much wraps up this